Howdy, this is our project report number 4. Um, Next slide. For this agenda, we're going to be talking about the motivation for the project, the methodology behind it, how we implemented it, as well as the demo and the respective results that came out of it.
So for the motivation, hardware Trojans have become a significant and growing concern in the field of hardware security. These are malicious modifications intentionally embedded into integrated circuits during the design or manufacturing process. So the risks they pose are substantial as they can degrade system performance, leak sensitive information, and disrupt critical functions. This is especially alarming, especially in industries where security and reliability are non-negotiable, such as military operations, financial systems, and healthcare devices. Despite the importance of detecting these threats, the current methods fall short of addressing the challenges posed by these modern complex hardware designs. Manual code reviews are tedious, time-intensive, and simply not scalable to meet the demands of today's integrated systems. Alternatively, there are other methods that rely on golden references. These are trusted Trojan-free versions of design. These are becoming less practical due to the increasing use of third-party intellectual property in the semiconductor supply chain. This brings us to the core motivation behind this project. So this project is built around the foundation of making a scalable, automated, and efficient approach to hardware Trojan detection. The complexity of hardware systems is growing, and our detection methods must evolve alongside. This is where machine learning, particularly graph neural networks, provides a promising solution. By representing hardware designs as data flow graphs and leveraging the power of GNNs or graph neural networks, we can automate the detection process, eliminate the dependency on unreliable golden references, and significantly improve both speed and accuracy upon detection.
So as we know, hardware Trojans are malicious mods that are put into hardware during the development process. They can also degrade performance, leak sensitive data, or disrupt functionality in general. And the increasing use of third-party tools and designs makes these vulnerabilities worse, making HT or hardware Trojans detection a critical but challenging task. To address this, we propose using graph neural networks to detect hardware Trojans at the register transfer level. By converting RTL code into graph representations, our approach leverages the structural relationships in hardware designs to identify patterns indicative of HDIs without relying on trusted reference designs. Tools that are shown in our report, like PyHDI, PyVerilog, and HW2Graph, are used to parse Verilog code and generate data flow graphs. These graphs are then processed through our architecture in the graph neural network, which includes increasing convolution layers, pooling, and a multi-layer perceptron for classification. Training data from sources like TrustHub is used to optimize the model's accuracy through hyperparameter tuning with different learning rates, epoch counts, and hidden layer configurations. And finally, our findings show that increasing the depth of convolutional layers and adjusting training parameters can enhance the detection accuracy of hardware Trojan infested circuits. And this scalable and automated approach provides a very good alternative to traditional methods, significantly improving the security and reliability of hardware systems while reducing reliance on time-intensive manual processes.
To optimize our hardware Trojan detection model and evaluate its performance across the various configurations, we developed an automated workflow using a custom Python script. Um, this Python script was designed to execute the experiment 50 times, iterating through different configurations. Each run adjusted key parameters such as the number of hidden layers in the model, learning rates, and the number of training epochs. We tested hidden layer configurations ranging from 1 to 4 to understand the impact of the model complexity on accuracy. Um, then we adjusted learning rates to zero point zero 0.01, zero point zero 0.02, and zero point zero zero 0.005 to observe their effect on convergence and stability during the training. The EPCO's counts were also stepped to ensure the balance between underfitting and overfitting.
All right. So now I'll start with the project demo. So first things first was we had to create a conda environment because there's a lot of Python libraries and dependencies we had to take care of. So after cloning the repo, this is where the code was to run the graph and the tree and pre-trained model. So what we did first was we edited the Python layer by messing around with the Python code by messing around with the hidden layers right here. And then we would also change the hyperparameters of the model, right? So that is these values right here. And there are different values that we wanted to test out, but we wanted to see how we wanted to make sure that we kept the independent variable to one thing, right? So what we do is after changing the models, we created a script that would run the simulation 50 times, you see right here, and it would keep track of all the run data and it would get the average at the very end. So an example of that running would be seen right here. And the command line arguments are the directory you want to save it in. So I'm going to run it, and so I want to save the results in a directory called test. So these are the runs. And one thing we did is usually it would print out the output on the terminal, but we redirected that to a log file so that we can parse through it, so that we can have our script parse through the inputs at the end, the outputs at the end, and get the final data, right? The average, because as you see right here, uh, the train accuracy, it can change depending on each run, right? So give it a second. Yeah, so 0.889, 0.3889. And we chose 50 runs just to be as accurate as possible, right? And one thing is that we're running this on our local PC. So uh, so it's saved in the folder called test. And if you go here, let's do like run one log. So this is the progress bars that fill that print out when you're outputting it, when you're running it, but because it was redirected to a log file, it got kind of messed up. But the important thing is the data at the very end, which shows the train loss, the final train loss, train accuracy, and everything. And that's what we use to parse through and get the averages. And you can see that right here. Right here, right? So I'll do so yeah, every output just looks like this.
And then when it came to the results, we conglomerated all the data into 4 different graphs, highlighting each of the different independent points that we modified, consisting of the epoch count, the layer count, as well as the learning rate, because all of those are the most important parameters, at least for this model, to, I guess, target a higher accuracy than was initially achieved with the existing model. From this approach, we found a few pros and cons. From the pros, we found out that the existing learning rate was ideal. Whenever we went higher or lower, it caused below average results. There were edge cases, of course, where a certain combination of epochs or a certain combination of learning rates would achieve a higher accuracy. I do believe that was caused by overfitting of the model and the data that was given into the model. More epochs overall did increase performance. However, there was a negative effect if you didn't increase it enough. Again, I think this is due to overfitting, so there is kind of a sweet spot that you have to look at. When it came to the cons, high and low learning rates led to below average results. We also found that one hidden layer was actually the most ideal, as increasing the hidden layers, although seemingly would increase accuracy, it actually decreased the accuracy. This is also a good thing when it comes to the model size, since less hidden layers indicates a smaller model as well as a faster executing model. And then if we could show the graphs on the screen, you could see the four different graphs classified by the hidden layer counts, as well as the learning rates and the epochs, with the x-axis being the epochs and the independently colored lines being the learning rate. At the one hidden layer, you can see that when we have an extremely high learning rate, it jumps around quite a bit. Whenever the learning rate's extremely low, it barely moves. And we see this going across all the different layer counts. In some cases, the smaller learning rate actually leaves a significantly lower result, as seen in hidden layer or in the fourth graph where there's four hidden layers. You could see the average accuracy totaling up around 57%, while the other two runs, average runs, are much higher, around 72%. So from this data, you can see that more epochs typically leads to a better result, but not always. And this is indicative in the two hidden layers graph. You can see that for the 0.02 learning rate and the slower learning rate of 0.005, it is significantly worse than just having 200 epochs, which is where kind of the sweet spot of this comes into play. So the initial setup that they had was one hidden layer, as seen in the top left graph. When we increased the epoch count while keeping the learning rate the same, we managed to achieve the most optimal results out of all of the graphs present. So if we use this approach, keeping the hidden layer count as just one, increasing the epoch count to somewhere around 600, and keeping the learning rate identical to what was already given, we achieve the best results and best accuracy with the given model. Thank you.